So with that brief introduction of the binary number system, right, we'll formally look at, if I were given, a weight, a number, okay, let's take a number in decimal, okay, let's take the number 251, okay, and I want to see how do I convert this number to a binary representation, right. So that means I have to express it as k equal to 0 to n minus 1, okay. This k equal to going from 0 to n minus 1 means you are actually using n bits, okay. Now one thing you must get used to as an electronics engineer is to be able to count from 0, okay. The first array index in C programming also, if you would have noticed, does not start from 1, it starts from 0, right. So that's a very fundamental thing for electronic engineers that one must get used to very quickly, okay. So I'm going to represent it like this, bk to power k, okay. Now what I want to do, right, is I want to represent this number in the as a binary number, that is take the decimal number, which is what we did earlier also, but the algorithm we used was more of a binary search, which you probably will come across later in your course. What we did was we found out if the given number in weight was either greater than something or lesser than something. If it was greater, then we basically added more weights to it on the right hand side. If it was lesser, we removed the biggest weight, added something lesser, and this is called a binary search, right. So in some very few number of iterations you will actually get to the final answer, but you don't have to do that always, right. You can formally do the procedure that I'm going to mention now in order to convert a decimal number to binary, okay. So you take 251, okay, you are always going to divide only by 2, okay, you're going to divide only by 2 and then you're going to figure out what the remainder is, okay. So let's do that first, right. So I will write, so maybe I'll do this in a table, right. I'll do the number, I'll get the quotient, I'll get the remainder, and yeah, okay. So I have 251, I'm going to divide by 2, right, always. So if I divide 251 by 2, the quotient will be 125, because 125 times 2 is 250, the remainder is 1, right. Now I take 125 and again divide by 2, right. So what is the answer? I am going to get a, this is what, 62 times 2 is 124, right. I'll get a remainder of 1, okay. Then I again do this, I get 62 here, I divide by 2 and I'll get 31, but this time my remainder is 0, right. 32 times 2 is 62, right. Then I again take 31, divide by 2, I get 15, remainder is 1, right. Again I do 15 and then I divide by 2, I get 7, remainder is 1. I take 7, divide by 2, I get 3, remainder is 1. 3, divide by 2, again you get quotient of, you get a quotient of 1 and a remainder of 1, right. So effectively now what we have had, right, is the binary representation. So all you have to do is group these bits. This is your binary representation of the answer, right. Now the only question is in which order should you do it, right. So what we have done is we have started with 251. So let me write out the number like this, 251 to base 10, okay, I am writing the base at the bottom of this vertical line, is equal to 1 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 0, 1, 1, right. So, what does this mean to base 2? This is the binary representation of the number 251, okay. So, let us now go ahead and verify if this is correct, by the way, okay. So, what is this? If I take this number, okay, and I treat it as a binary number. So, how many bits are there? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 bits here, right. So, now what I am going to do is I am going to write this as so let me write this as 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So, 0 to 7 I am going to go with 8 bits, right. So, I have the answer 1, 1, 0, 1, 1, 1, 1, 1, okay. So, what is, I am now going to do the weighted addition and check the answer. I am first going to do only the weighted multiplication. 2 power 0 into 1 is 1, 2 power 1 into 1 is 2, 2 power 2 into 0 is 0, okay. So, I am going to add all this now. 2 power 3 into 1 is 8, 2 power 4 16, 2 power 5 into 1 32, okay, 64 and 128, okay. So, now I am going to add these numbers, and if I do add it, I should get 251 as the answer, okay. So, I basically have 128 plus 64, right, which is 188, 192, 192 plus 32, 192 plus 32 is 224, okay. 224 plus 16 is 240, then 248, 250 and 251. So, you can add for yourself and see that you get 251 as the answer. So, in order to convert a decimal number to binary, just follow this procedure that I have shown here, okay. Keep dividing by 2 and you basically will get the answer in a very straightforward manner, okay. The weighing balance example was only to give you an analogy so that you just understand the significance of the binary number system. So, in the electronic system thinking course, we had explicitly shown you that if you don't choose weights in the powers of 2, right, then you will not be able to represent every integer appropriately, right. So, therefore, this number system is very consistent and this is how you convert a decimal number into a binary representation, okay. So, what we have done is we have effectively been able to represent this as an 8-bit number. So, the n actually n equal to 8, okay, in this case, and we have been able to represent it as an 8-bit number. So, B0 to B7. Now, the question is, if I give you an n-bit number, right. Now, instead of let us say 251, suppose I had taken 500 and 511, right. Then how many bits would I need to represent the number 511, right. In general, you could also ask the other question. Suppose I give you an n-bit number, right, then how many bits do I need? I mean, what is the range of integers in the decimal system that this n-bit number can represent, okay. So, we will look at that question next. So, I have an n-bit number, okay. So, I am going to immediately say that my n-bit number is going to be represented like this: Bn minus 1, Bn minus 2 all the way to B0, okay. Just some terminology. when I look at this representation, I am going to write this as bn minus 1 into 2 power n minus 1 plus bn minus 2 into 2 power n minus 2 plus so on b0 into 2 power 0. Okay. So, when I write it, the reason I wrote it from left to right is this one is called the LSB, least significant bit. Okay, and this one is called the MSB, most significant bit. Okay. So, obviously the least and most makes complete sense here, because least is being multiplied by the least power of 2 power 0, and most significant bit is being multiplied by the highest power of 2, that is 2 power n minus 1. Okay. So, just by looking at this representation, right, you can clearly figure out what is the maximum and minimum number that can be represented in this n bit representation, right, maximum and minimum decimal number. So, this one, each term here, by the way, is a positive number, right, and we are adding n such positive numbers, right. So, if you look at what is the minimum value, right, the minimum value of any n bit binary number that we are going to represent is obviously if all the binary bits are 0. Okay. So, the minimum value, okay, is all bk equal to 0 for all k. Okay. So, there is b0, b1, b2 all the way to bn minus 1 are 0, in which case implies this binary number b, okay, b equal to 0, okay, in decimal. On the other hand, if you take maximum value, the maximum value again is, it's a sum of positive numbers, each number has to be at its maximum value, right, and for that to happen, each bit bk must be equal to 1 for all k, implies b is simply summation 2 power k, right. So, if you just write out this expansion with make all b0 to be n minus 1 as 1, this will be 2 power n minus 1 plus 2 power n minus 2 plus all the way to 2 power 0, right, and this is a geometric progression with the first term being 1 and the common ratio being r being 2. Therefore, you can write this, and how many such terms do we have? We have n terms. So, what is this value equal to? It is 2 power n minus 1, okay, divided by 2 minus 1. So, how did this come? If I have a geometric progression AR plus AR square plus AR power n minus 1, right, this will be A into R power n minus 1 by r minus 1, if you remember your geometric progression from class 12. So, therefore, you use this result and plug it in here, you will get the answer is 2 power n minus 1. So, the maximum value that can be represented by an n bit binary number is 2 power n minus 1. Okay. Now, in order to, of course, convert a decimal number to binary, coming the other way, if I want to come from the decimal number to binary, you keep dividing by 2, and how many ever bits you get, okay, you will basically, you keep dividing until the remainder, right. Remember, when we did this division, we did it until the quotient itself, right? That's how you do division, by the way, even in decimal, right? Until the quotient itself is less than the base of the number system, which is less than 2, right? So here I have to wait until the quotient either goes to 0 or quotient goes to 1, and then I take the bits that I get, and how many ever bits I get, that means that is the representation of that number, right? So now what you can do is, you can take a decimal number, you can represent it as an n bit number, and let's say that I take a number b in base 10 and represent it as b0, okay, where n is the minimum number of bits that are needed in order to represent this as an n bit binary number, right? So n is chosen so that you are able to accommodate that number. See, for example, if I take the 251, right, I cannot represent this with just 4 bits or 5 bits. I need at least 8 bits, right? And so if I now take an 8-bit number, right, so you take this 251, we need at least 8 bits are needed for it, right? Now, what is the range of an 8-bit number? It is 0 to 2 power 8 minus 1, okay? What is 2 power 8? It is 0 to 256 minus 1. So 0 to 255, okay? So therefore, 251 falls in this range 0 to 255, and it is evident that I can represent it with just 8-bit information, right? Now, if I want to take this n-bit representation and I want to expand it to, let's say, a 2n-bit representation, okay? Because one common thing that we would do is we might want to add 511 plus 251, okay? So when you do the binary representation for 251, you will find that the minimum number of bits that you need to represent 251 is 8. We already saw that, 8 bits. So you will represent this as B7, B6 all the way to B0. Now, you do the same representation for 511, right? 511, you just continue doing your division, okay, and you see what number you get. You will find that you need 9 bits, okay. So let me call this as some other binary number, but I will call it C instead of B. So I have C8, C7 all the way to C0. So if I want to now add this, 9-bit number with an 8-bit number and all that, it is necessary for me to represent both these numbers in the same number of bits so that I can operate on them. So many times you will land up in a situation where you have to represent a lower bit number, right, a lower bit representation number using higher bits. The opposite is not possible. I cannot represent 511 with 8 bits, right, but I can represent 251 with 9 bits. And how do you do that? If you look at the representation, right, so 251, I am going to write this as bk into 2 power k equal to 0 to 7. Now what do I want to do? I want to add another bit, right, the 9th bit to this representation, okay. So I have to write this as b8 2 power 8 plus summation k equal to 0 to 7 bk 2 power k, okay. Obviously I have to set this b8 equal to 0, okay. So if I set that to 0, the 9th bit, right, if I set that to 0, then effectively only the bottom 8 bits will always matter, and there is nothing surprising in this. in the decimal number system, right from school days you have been taught that adding zeros before do not matter, do not alter the value of your number, even in the decimal number system. That's exactly what we are doing here. So if I take a binary number, right? So if I take this number here 111511011, right? So if I take this 251, I will represent it as 011. Then in order to represent it as a 9-bit number, I'll have to add a 0 here. Remember, you cannot add a 0 here because that will change the value of the number system. That's like adding a value. If you have the number 10 in decimal, if you add a number before to the right, it will become 100. But if you have a 0 before 10, then the number will be 010 where the value does not change. So I can add any number of zeros here in order to convert a lower bit representation number to a higher bit representation number, right? So that is the overall picture of the binary representation of decimal numbers, and very importantly, this whole thing is basically an unsigned representation. Okay, this is an unsigned representation, and which basically means that all numbers here are treated as positive numbers. Okay. So now, having represented the integers in this way, what about fractions, right? So let's say, so I am now going to deal with fractions. So let's say I have the number 21.25. Okay, I can write this as 21 plus 0.25. Okay, now this one can be converted to a decimal number. Okay, so let us see. First of all, you take 21. Okay, divide by 2, you will get 10, remainder 1. Okay, this is the number, this is quotient, remainder, right? And then I take 10, I divide by 2, I will get 5, 0. Then I take the quotient again, I divide by 2, I will get 2, 1. I get 2, I get quotient of 1, remainder is 0. Okay. So therefore, what you see here, I can write this. So 21 to base 10 is equal to 10101, right? So what is this? So this is 2 power 0, this is 2 power 0, 1, 2, and this one is 2 power 3. So it is 8, no, 2 power 0, 1, 2, no, this is 2 power 4, I am sorry, 2 power 4, right? So therefore it is 2 power 4, 16 plus 4, 20 plus 1, 21, right? So effectively I have this as my binary representation of 21, and just like you do in fractions, right? So here, what does this actually mean in the decimal number system? It is 10 power 1 into 2 plus 10 power 0 into 1 plus 10 power minus 1 into 2 plus 10 power minus 2 into 5. Okay, and you add all of this, you will get this is 0.2 and this is 5, right, 0.05. Okay. So similarly, what we are going to do now is to take this fraction here, okay, and we are now going to represent it in powers of 2. Okay. So this one we said was summation bk to power k. Okay. The fractional part, if I want to add, I just have to say it is bk to power minus k. Just like the decimal number system, you come to 10 power 0, then you go to 10 power minus 1, 10 power minus 2 and so on, right. So, effectively if you take 0.25, this is basically 1 by 4, right. This is 1 by 2 power 2, okay. And therefore, you can write this now, the fractional part 0.25 to base 10, you can write as 0.0, so 2 power minus 1, 2 power minus 2, 1, okay, and which implies 21.25 to base 10 will be equal to 10101.01 to base 2, right. So, this one is 2 power, let me just, this is 2 power minus 2, 2 power 0, 2 power 1, 2, 2 power 4, right. So, effectively the fractional representation is just a logical continuation of your integer part, just like you do in the decimal representation. So, we will do a lot more examples of these in the assignments and in the practice problems, and you will get very comfortable with this representation going forward. Okay. Yeah, thank you.